Hello, everyone. Welcome to today's lecture on infrared spectroscopy, focusing on two critical components, choppers and detectors. These elements are essential for enhancing the precision and sensitivity of your spectroscopic analysis. Let's get started. So, here we're exploring the fascinating world of infrared spectroscopy. This powerful technique measures how materials absorb infrared light, revealing their molecular structures. For accurate results in IR spectroscopy, two elements are crucial: signal modulation, which is handled by choppers, and signal detection, performed by detectors. In this presentation, we'll dive into the roles, types, and benefits of these essential components, ensuring you understand how they enhance the precision and sensitivity of your spectroscopic analyses. Let's start with IR choppers. These essential devices modulate the infrared light, which helps in reducing noise and enhancing the clarity of the detected signals. By intermittently blocking and allowing the IR beam to pass through, choppers effectively convert a continuous signal into a pulsed one. This modulation is crucial because it allows the system to better differentiate the actual signal from background noise, leading to more accurate measurements. This process is particularly important in Fourier transform infrared, or FTIR, spectrometers. In these advanced instruments, the precision and sensitivity of the measurements heavily depend on the ability to isolate the true signal from any noise, and that's exactly where choppers come in. They ensure that the data collected is as clean and precise as possible, making them a fundamental component of the IR spectroscopy setup. Now, let's discuss the role of choppers in infrared spectroscopy. Choppers perform two primary functions. First, they modulate the IR light, which is crucial for reducing noise in the system. By converting a continuous light signal into a pulsed one, choppers help in isolating the desired signal from unwanted background noise. This leads to clearer and more accurate measurements. Second, choppers play a critical role in differentiating the actual signals from background noise, ensuring that the data collected reflects the true characteristics of the sample being analyzed. These functions are particularly essential in Fourier transform infrared, or FTIR spectrometers. In these sophisticated instruments, the precision and quality of the measurements rely heavily on the chopper's ability to modulate the IR light and reduce noise, making choppers an indispensable part of the IR spectroscopy setup. This process is particularly important in Fourier transform infrared, or FTIR spectrometers. In these advanced instruments, the precision and sensitivity of the measurements heavily depend on the ability to isolate the true signal from any noise, and that's exactly where choppers come in. They ensure that the data collected is as clean and precise as possible, making them a fundamental component of the IR spectroscopy setup. Choppers are essentially mechanical devices designed to intermittently allow or block infrared light as it passes through the beam path. Typically, they work by spinning or oscillating, creating a modulated beam that alternates at a specific frequency. This frequency can range from about 10 Hz to 100 Hz, depending on the setup. The key here is that this modulation of the beam helps create a distinct, alternating signal that is easier to analyze. As we discussed earlier, choppers are devices used in infrared spectrometers to modulate the infrared light, making it easier to detect the signal from the sample while filtering out background noise. There are different types of choppers, each with its advantages and specific use cases. Let's go over them one by one. The first type is the mechanical chopper. These are the most traditional and widely used choppers in infrared spectroscopy. A mechanical chopper consists of a rotating disc with slits that intermittently allow and block infrared light as it spins. The rotating disc controls the timing of the modulation. alternating the light between on and off states at a set frequency, usually between 10 Hz to 100 Hz. These devices are typically simple and inexpensive, which is why they are so commonly used in conventional setups. However, because they have moving parts, there can be limitations when it comes to precision and longevity. The second type is electro-optical choppers, which are a more modern approach. Unlike mechanical choppers, electro-optical choppers have no moving parts, making them more durable and precise. These choppers utilize Pockels cells or acousto-optic devices to modulate the light. Pockels cells work by applying an electric field to a material, which changes the material's refractive index and modulates the light. Acousto-optic devices, on the other hand, use sound waves to diffract and control the light beam. These choppers are capable of operating at very high frequencies, providing excellent control and stability. Next, we have optomechanical choppers, which are a hybrid of mechanical and electro-optical choppers. These systems combine the precision of electro-optical devices with the modulating ability of mechanical systems. The goal is to improve performance by offering greater precision while maintaining the modulating effect of mechanical choppers. In these systems, a mechanical disc or mirror is used to modulate the beam, while electro-optical devices fine-tune the modulation for even more accuracy. This hybrid approach is ideal for high-precision measurements in complex spectroscopic experiments. Let's quickly recap the three types of choppers we've covered today. Mechanical choppers, simple and cost-effective, but with moving parts that limit precision. Electro-optical choppers, no moving parts, providing precise modulation with high-frequency control. Optomechanical choppers, a hybrid system combining the best of both mechanical and electro-optical choppers for enhanced performance. So, how do you choose the right chopper for your needs? Well, it depends on the specific requirements of your spectroscopic setup. For general purposes, mechanical choppers might suffice. However, if you need higher precision, durability, and faster modulation, electro-optical choppers are the way to go. And for highly specialized applications, optomechanical choppers provide the ultimate in precision and flexibility. Why are choppers necessary? In infrared spectroscopy, one of the biggest challenges is ensuring the accuracy of the signals you're measuring. Background noise, like electrical interference or environmental vibrations, can easily overwhelm the sample signal. This is where choppers come in, modulating the infrared light to make the signal clearer and easier to analyze. Now, let's talk about the specific benefits of using these devices. The first major benefit of using choppers is the elimination of background noise. As we know, noise can come from many sources, including fluctuations in the light source, ambient light, and even electrical noise from the equipment. Choppers modulate the infrared beam, which allows the detector to focus on the modulated signal and ignore constant background noise. This ensures that only the signal of interest is measured. By blocking out unwanted noise, choppers make your measurements more reliable and the overall spectroscopic process more accurate. This leads us to the second major benefit, improved signal-to-noise ratio, SNR. The signal-to-noise ratio refers to the amount of desired signal compared to the background noise in your measurements. When choppers modulate the light, the detector can clearly differentiate between the signal and noise, which leads to a higher SNR. A better SNR means more accurate results, allowing you to make better conclusions from your data. This is especially important when working with weak signals or when precision is critical, as in medical or environmental testing. Another significant benefit of using choppers is their compatibility with detectors that require modulated light, such as pyroelectric detectors. These detectors are designed to detect changes in infrared light over time, which is exactly what choppers do by modulating the light. Without this modulation, the detector would have difficulty distinguishing the signal from constant light exposure. How placement and frequency work together. We'll quickly go over the placement and frequency of choppers in infrared spectroscopy, which are key factors in optimizing signal modulation. Choppers are typically placed between the IR light source and the beam splitter. This ensures the light is modulated before reaching the sample, allowing for cleaner signals to be detected by the instrument. Host. The chopping frequency is usually between 10 to 100 Hz. The frequency depends on the detector's response time and the requirements of your experiment. Faster detectors may require higher frequencies, while slower detectors benefit from lower frequencies. The correct placement ensures effective modulation, while choosing the right frequency maximizes the signal-to-noise ratio and detector efficiency. Always adjust these factors based on your setup. Next, we're going to talk about infrared detectors, devices that convert absorbed IR light into measurable electrical signals. These detectors are essential for capturing the data from your sample in infrared spectroscopy. Let's explore the different types of IR detectors and how they work. IR detectors can be classified into several categories based on their operating principles. Let's take a look at the main ones. Thermal detectors detect changes in temperature and are useful for broad spectral range. Photon detectors respond to individual photons and offer high sensitivity. Photoconductive detectors detect changes in conductivity when exposed to infrared light. Photodiodes generate electrical current when exposed to infrared light, widely used in precision measurements. Quantum detectors, the most sensitive, using quantum principles for precise infrared detection. We'll now discuss an essential aspect of infrared radiation detection: thermal detectors, their operating principles, and the common types. Thermal detectors play a pivotal role in sensing temperature changes caused by the absorption of infrared radiation. Unlike photon detectors, which directly respond to individual photons, thermal detectors measure the heat generated when infrared radiation is absorbed. This makes them incredibly versatile for various applications, including medical diagnostics, industrial monitoring, and even space exploration. First, let's talk about thermocouples. These detectors operate based on the Seebeck effect. When two different conductive materials are joined and exposed to temperature differences, a voltage is generated which correlates to the absorbed infrared radiation. Thermocouples are robust and widely used for their simplicity and reliability. Next, we have thermistors. These are temperature-sensitive resistors, and their resistance changes significantly with temperature. When infrared radiation is absorbed, the temperature of the thermistor increases, causing a measurable change in resistance. Thermistors are highly sensitive and are often used in applications requiring precise temperature readings. Pyroelectric detectors. Finally, pyroelectric detectors. These detectors leverage the pyroelectric effect, an intrinsic property of certain materials that generate an electric charge when subjected to temperature changes. Pyroelectric detectors are highly responsive and are commonly used in motion sensors and thermal imaging devices. We're now diving into the world of thermocouples. If you've ever wondered how we measure temperature in some of the harshest environments or in scientific research, this video will clear things up for you. Let's get started. A thermocouple is a device used to measure temperature. It works based on a pretty interesting principle: voltage generation from the temperature difference between two dissimilar metals. When these metals are joined together, a small voltage is produced, and this voltage can be used to determine the temperature at the junction. This is what's called the Seebeck effect. Simply put, When one end of the thermocouple is heated and the other stays cooler, a voltage difference is created. This voltage is directly related to the temperature difference. Now, thermocouples typically measure temperature in the mid-infrared range, which is between 2.5 and 50 micrometers. This makes them ideal for use in high-temperature environments, like furnaces or kilns, or in scientific research dealing with infrared radiation. One of the great things about thermocouples is that they're simple, inexpensive, and robust. They're easy to use and install, meaning they don't require complex setup. Plus, thermocouples are incredibly durable and can withstand tough industrial conditions, which is why they're used in so many fields from manufacturing to research. However, thermocouples do have their drawbacks. For starters, they're less sensitive than other temperature sensors. The voltage they produce is relatively small, making them not the best option when you need high precision. Also, they tend to have a slower response time. So, if you need to measure temperatures in a situation where it changes rapidly, thermocouples might not be the best choice. Even with these disadvantages, thermocouples are still widely used in many applications. They're used in industrial temperature monitoring, furnace and kiln operations, even in scientific research. Thermocouples are great for those environments where you need something that's reliable, cost-effective, and can withstand extreme conditions. We'll next talking about photon detectors and how they work to convert infrared, IR photons into electrical signals. I photon detectors are devices that directly convert incoming infrared photons into an electrical signal. Unlike thermal detectors, which rely on temperature changes to measure light, photon detectors capture the actual photons and use them to create an electrical current. Essentially, when an IR photon hits the detector, it excites electrons, causing them to move and generate a measurable electrical signal. One of the biggest advantages of photon detectors is their high sensitivity. They're much more sensitive than thermal detectors, which makes them ideal for detecting weak signals in low light or faint IR scenarios. These detectors are used in everything from astronomy to security cameras, helping to detect faint signals that would be missed by other sensors. Photon detectors are amazing tools for converting light into data, especially when dealing with weak signals. We'll next talking about photon detectors and how they work to convert infrared, IR photons into electrical signals. I photon detectors are devices that directly convert incoming infrared photons into an electrical signal. Unlike thermal detectors, which rely on temperature changes to measure light, photon detectors capture the actual photons and use them to create an electrical current. Essentially, when an IR photon hits the detector, it excites electrons, causing them to move and generate a measurable electrical signal. One of the biggest advantages of photon detectors is their high sensitivity. They're much more sensitive than thermal detectors, which makes them ideal for detecting weak signals in low light or faint IR scenarios. These detectors are used in everything from astronomy to security cameras, helping to detect faint signals that would be missed by other sensors. Photon detectors are amazing tools for converting light into data, especially when dealing with weak signals. MCT, or mercury cadmium telluride, is a semiconductor material that generates carriers when exposed to infrared radiation. Essentially, when IR photons hit the MCT, they excite electrons, creating an electrical signal that can be measured. MCT detectors are ideal for the mid-IR range, specifically between 2 and 25 micrometers. This makes them perfect for applications where mid-infrared light is needed, like in FTIR spectroscopy. One of the biggest advantages of MCT detectors is their very high sensitivity. They're excellent at detecting faint IR signals, making them a top choice for FTIR spectroscopy, where precision and sensitivity are key. In short, MCT photon detectors are fantastic for sensitive mid-IR applications, from scientific research to industrial analysis. Photoconductive detectors are based on a simple principle. When IR radiation hits a material, it causes the material's electrical conductivity to change. Essentially, the IR photons excite the electrons in the material, allowing them to flow more easily, which changes the material's resistance. One example of a photoconductive detector is the bolometer. This device detects changes in resistance caused by temperature changes due to infrared radiation. As the bolometer absorbs infrared light, it heats up, and its resistance increases, which can be measured and used to determine the intensity of the incoming infrared radiation. Photoconductive detectors, like bolometers, are used in various applications, from thermal imaging to environmental monitoring and scientific research, offering a way to detect and measure infrared radiation. Next, we're diving into the world of quantum detectors and how they're revolutionizing the way we detect light and other types of radiation. Quantum detectors use the interactions between photons, or light particles, and special materials to detect extremely faint signals. These detectors rely on principles of quantum mechanics, allowing them to sense even the weakest photons. One of the biggest advantages? Extreme sensitivity. Unlike traditional detectors, quantum detectors can pick up incredibly subtle signals, making them perfect for applications in fields like astronomy, medical imaging, and deep space research. A great example of this technology in action is superconducting detectors for far infrared radiation. These detectors operate at very low temperatures and can detect far infrared radiation, which is often challenging for regular detectors. So, whether you're exploring the depths of space or looking for the faintest signals, quantum detectors provide unmatched precision. Today, we have discussed how two key components, choppers and detectors, work together to enhance IR spectroscopy. In IR spectroscopy, choppers modulate the IR light to improve signal quality and reduce noise, while detectors convert those IR signals into measurable outputs. Together, they work in tandem to greatly enhance the precision and sensitivity of IR spectroscopy. First, we talked about choppers. These devices modulate infrared, IR light, to improve the quality of the signal and reduce noise. By cutting off or modulating the light at a specific rate, they make it easier to focus on the relevant data. Next, detectors were studied. They convert the IR signals into measurable outputs, with different types designed for specific applications. This allows for precise readings and tailored results based on what's needed. When combined, choppers and detectors significantly enhance the precision and sensitivity of IR spectroscopy, making it a powerful tool for research and analysis. In conclusion, infrared spectroscopy relies on the perfect synergy between advanced choppers and detectors. Understanding the unique roles of each component, whether it's chopping the IR beam or detecting the radiation, is crucial for obtaining high-quality data in any analytical application. By selecting the right choppers and detectors for your specific needs, you ensure accurate, reliable results for a wide range of scientific and industrial processes. Thank you for watching and joining me today. I hope you found the content valuable and informative.